Thank you very much. Ladies and gentlemen, welcome to my speech. It's an honor for me to be invited to this forum and to give you my speech about the future steelmaking technologies and how we in Europe try to meet the climate target by CO2 lean steelmaking. Yeah, about climate change. We have spoken about climate change already several times during this forum. It is evident that we have a climate change, that we have a change in the temperature. This first slide shows you a temperature recording from Vienna since 1775 till the year 2019. This shows you, each stripe shows you the average temperature of the year, and there is a comparison to the average annual temperature in the period of 1971 to 2000, and blue means colder, and red means hotter, and you can see dramatically what happens in the last 20 years. You have a lot of red stripes. We can see as evidence of this temperature measurement that we have an impact, obviously, or this is higher CO2 content in the atmosphere on the temperature. Yeah, we have to do something. Yeah, we have already agreed on the Paris Agreement 2015 that we have a clear climate target. We would like to meet the temperature increase by 2 degrees in comparison to the temperature level before industrialization. And there are also action sets from the political side. This is the European Green Deal in 2019. This defines that Europe has to be transformed CO2 neutral, no greenhouse gas emission until 2015. And if I look at now our own company, Austrian government, Olga have launched a program last year, 100% renewable energy for the electric energy production in 2030 and climate neutrality already 2040. And this means, of course, for the steel industry, we have to act, not react. I say was act, and we have to do something. This is a summary of what we are doing in Europe about CO2 mitigation. Mr. Martinez and Mr. Petermay already introduced the part of that, what is going on. This is process integration. That means all the activities we are talking about to improve existing technology. How can we reduce the CO2 emission, including carbon capture and storage, also carbon utilization. We heard before about that. What can we do to produce chemicals out of the CO, carbon monoxide and CO and carbon dioxide from gases from the steel industry. And I will now keep my focus on hydrogen, using hydrogen, in particular on technologies which are not now available industrial scale, which has a technical readiness level below 7-8. End of place. Also, there are activities about using directly electric energy. And important topic for me is the circular economy. This will definitely be a very important topic for meeting the CO2 targets, especially in the next 10 years, 15 years. That means in recover from residues, increasing the scrap rate. This will be the topic. Yeah, this is maybe also known. These are this slide represents the 4 steel routes, which steel making routes, which we have available. This is the integrated route, symmetric reduction route, direct reduction route. These are the 3 routes which are based on iron ore for producing crude steel, and then we have the recycling route based on scrap. And if you look at this slide, I have indicated the potentials of hydrogen use in these routes. The integrated route, we can say about 10% of hydrogen can be used to substitute carbon as a fuel. The route which is now available for using hydrogen to a higher extent, up to 100%, is the direct reduction technologies, especially we have heard about Midrex, energy iron. These are technologies which are now available. The problem is not the technology to produce steel with hydrogen. The problem is to have hydrogen. And yeah, this is now comes me to the issue. What are the topics we have to face? Because we as the steel producers, we can do, but what we need is we have a production. We have to produce hydrogen, and there are electrolyzer we need to produce hydrogen from water electrolysis by renewable energy. It should be CO2 free. That means we need renewable electric power. Hydrogen production from biomass would be an alternative, but I think it's quite limited to consider it for steel industry, because this is a quite huge amount of biomass which you need. A further topic already addressed is definitely the storage of hydrogen. This includes gaseous storage, it includes in liquid state storage. There are a lot of research going on, but this is a topic which is not solved now. Especially if we look for the demand of hydrogen for the steel industry, smaller storage available, but if think about traffic, the storage is solved, but not for the steel industry. And distribution is a further topic. We have to distribute, we have to supply the hydrogen from the production to the steel plants. And we have to deal it, we have to compress it. These are the topics we are focusing on if we speak about hydrogen use in the industrial sector in the size of steel industry. Okay, but I'm representing K1-Met, and K1-Met is already active in the production of hydrogen. There is one pilot plant it's a flagship project from Europe. It's called H2 Future. There's a pilot plant at voestalpine site in Linz. This is a so-called proton exchange membrane electrolyzer, which has 6 megawatt power and is producing 1,200 cubic meter of hydrogen. Partners are Verbund, this is the Austrian electric power supplier, Siemens, Austrian power grid supplier, K1-Met, TNO, we heard before, representative from TMO, and voestalpine are the members of this technology. Yeah, the aim is to demonstrate the operation of this PEM electrolyzer in the environment of a steel industry, which should simulate also the different supply from power from the grid. That means typically fluctuating power supply from grid due to renewable energies. And this was quite well demonstrated. They could run stable operation between 1.5 megawatt up to 9 megawatt. And what is very was for me astonishing is the good efficiency what they achieved, more than 80%. It was a target about 80%, they achieved 83% as a stack efficiency. And the purity of the hydrogen is also excellent, as well as of the oxygen. Yeah, this picture already was shown before. I can just was mentioned from the previous session. What are the potential to reduce the CO2 emission in comparison to the integrated route? First step, natural gas with direct reduction electric arc furnace, reduction potential 35 to 40%. And if we go for pure hydrogen with electrolyzer, direct reduction shaft and electric arc furnace, we can achieve 80% or less. Yeah, what are the potentials we have if we use hydrogen? We spoke about the technologies nowadays. You can see here, maybe it's a diagram which metallurgical guys like very much. May you excuse me for non-metallurgists. It's a combination of two phase diagrams, with the iron-carbon diagram and the iron-oxygen diagram, and it illustrates how we produce nowadays steel. The gray lines represents the integrated route. You start with the iron ore, then you convert the iron ore in a blast furnace to hot metal with a significant amount of carbon, up to 4.5% carbon, and then later you go to the basic oxygen furnace and to remove the carbon and to make out of crude steel. It's a two-step process. Yeah. What is available now as an alternative is the blue line. It's hydrogen-based direct reduction. It is converting the ore to a so-called DRI, direct reduced iron. And this direct reduced iron you then melt in electric arc furnace to steel. This is what is available nowadays. But the future, and this is the way why we use hydrogen, is the way that you can do it in one step. You can go directly from the iron ore to steel in one process step, and we can avoid these two steps which we have now in future. Yeah, and this is a topic we are researching on in this so-called SUSTEEL or sustainable steel. This is a hydrogen plasma sweating reduction technology where we use ultra-fine ore. This is pellet feed, which we reduce in ionized hydrogen. This has the advantage. Ionized hydrogen is a very strong reducing agent, which is much stronger than carbon, and we can do it in one step to produce out of them steel. This is already demonstrated that it's working. This is a breakthrough technology. We have a pilot plant at voestalpine Stade-Donawitz site. This is a consortium where K1-Met, voestalpine, and also the university in Leoben are involved. We are still in a small scale. The technological readiness level is around 4 to 5. That means we need additional years until to come to maturity, but we think this will be successful. Another technology which already was introduced, Mr. Petermeier, is the HYFOR technology, hydrogen-based fine ore reduction. This is the lead has primetals, but also K1-Met and voestalpine and also the university in Leoben are involved. They demonstrated already that they can produce DRI from fine ore, which is also pellet feed fine ore. This you are avoiding here also the agglomeration step. And they are also running this pilot plant in the voestalpine site in Donawitz. And they are now doing these tests to get the basis for the scale-up, for the next scale-up step. Yeah. What can you expect in the future for introducing hydrogen-based steel making? Hydrogen is I think it's last, yeah. Nearly last. Yeah. This is the challenge of what we think about. This is already, I think, produced before. We start with the implementation of a natural gas-based direct reduction, and then we can switch over stepwise to 100% hydrogen. But the alternative will be, maybe this is a vision for the next 15 years, and to install instead of this integrated route, a one-step process which is based on hydrogen plasma sweating reduction. This is what we think. I will not explain this slide because this was already discussed, all the topics about the future challenges and the opportunities and constraints. This is summarized what the speakers before already mentioned. There are constraints, but also opportunities. We see strong opportunities with hydrogen in steel making. Okay, then this will be my last slide, the transition to 2050, and we think after 2035 we will also be ready with our technologies we are now developing on hydrogen-based steel making, and will be available for the implementation. Thank you very much for your attention.